was thinking, no, Sue should be right, because like, the lights are also moving, but they're only flashing once. They flash, right?
Yeah,
So like, that's instantaneous from that moment. It's not like the lights are not moving with the detector. So it should hit, the light from the right light should hit the detector first, but I don't know. Cause it's so fast that I'm like, does it make a difference?
it does. Well, let's assume that we've got precision. The thing has been done so incredibly precisely. It's what is known as a thought experiment, so we could make it as ideal as we want. Or a Gedanken experiment.
I wanna say Lou is right then.
So we have 2 votes for Lou. Harrison, do you have a reason for why Lou's right?
Other than I'm Lou and it's what I saw.
Okay. But when I was doing Sue, that
That
worthless?
That didn't resonate with me. My
It
twin
didn't
sister.
resonate.
My twin sister is nothing to me.
It could be just my acting. All right.
Yeah, I guess I'll vote Lou too.
Well, I guess it depends on,
You know what we could add to this problem? We could make it a trolley problem. Have some people on the tracks, on the train tracks.
No.
Yeah.
Let's not complicate this one too much at the
I just
moment.
okay.
All right, I will say Lou it will be green. What's wrong with Sue? How could Sue be wrong? Because again, it's all from her point of view, the 2 lights, everything's at rest relative to her. Why would the lights not get to the middle at the exact same time?
She's not proper.
yeah, she's not proper.
She's not in the proper frame.
Which is different than she's not proper.
Yeah.
I was being dramatic.
Wow.
She's not, I think she's not proper.
I forgot what the word was, so I was just gonna say not proper too,
But
so Anna.
All of that stuff, the 2 things that flash, Sue, none of that is moving. So in terms of this, she is proper in terms of this. Because all of this is at rest relative to her.
Right, but is that the proper frame for the whole problem?
In terms of, the detector would be it's in her frame, so, yeah. The detector is moving relative to Lou, so Lou cannot have the proper view of the detector.
So somebody could really argue that Sue is right.
Except she's not.
Okay.
That's my reasoning.
How on earth could Sue be wrong? So think about it this way, you're in a room, nothing's moving relative to you. You got a detector smack dab in the middle of the room, 2 lights go off at the same time. Doesn't it make sense that those 2 lights would get to the detector at the exact same time? I got one person who says yes.
It would make sense.
It does make sense.
Okay. But since they don't get there at the same time, how on earth could that happen?
If you're moving, because the train is moving to the right.
But from Sue's point of view, Sue is absolutely right that everything is at rest relative to her.
Everything? Like,
Everything at the train car, everything in or touching the train car. Let me reword that for the literalists. The train car itself and everything inside the train car and attached to the train car and Sue are all at rest relative to each other.
It seems like there's an external force that may not be a part of their like little internal whatever of the train car and Sue. And that external thing, which in this case is the velocity, is impacting, in this case, the light.
Not an external force involved in this one, unless you really want to overcomplicate it.
okay, but like,
There's a simpler reason that students have usually struggled to figure out. All right, so again, detector smack dab in the room, everything's at rest. How could one light from one side get to the detector before the other side?
well, something has to be moving, because you hit the detector. That's the point.
I mean, the light moves once it flashes, but other than that, everything's at rest.
Oh, because the light from one of the lights versus the other are actually moving at different. Wouldn't they be moving at different speeds, even within her train car?
Then you are suddenly going with that Einstein was completely wrong. His interpretation
There is
was
no
wrong.
such thing as the speed of light.
But it,
And special relativity is complete bunk. And Hall and Rossi are just shaking their heads right now. Going, who
I'm
raised
so
you?
sorry, everyone, I'm sorry, I failed you.
No, the light is traveling at the same speed.
It's not like one of them is sped up or slowed down because the train car is moving.
No, that's one of the deals with special relativity is the idea that despite how it's moving, the light will still seem like the light will always travel at the same speed.
Does this have to do with the twin paradox of like there's a velocity involved?
Not a twin paradox issue. Completely different issue.
I need you to break it down for me again.
All right, so
Break it down.
detector smack dab in the middle of the room,
Detectors in the
everything's at
middle.
rest.
Everything's at rest.
I'm gonna have light flashing off of both sides.
Yep.
One of the light will get to the middle first. And there's a very simple solution to why, or how that could happen. Not necessarily simple conceptually, but there is a simple solution if you just strip away all the things I'm not including in that scenario I just gave. Because some people tend to still think about the original problem instead of the new problem I just gave. I have light that's gonna go off on both sides. I got a detector smack dab in the middle. The light from one of the sides will get there before the other side.
It has nothing to do with the fact that the middle has moved relative to Lou.
Nothing to do with that.
I'm just hung up on how, I don't know how you would hit the detector in the first place if nothing's moving.
Alan,
How would you hit the detector in the first place if nothing's moving
the
relative?
light moves. Sorry, the light will move. Once the light flashes, the light does travel through space. It takes a certain amount of time for light forms, when it's flashed, to hit the detector.
Are you asking us to consider this problem as if the train car were not moving and this was still happening?
If the train car is not moving, what I'm saying, from Sue's point of view, the train car is not moving. That is absolutely correct.
Yes.
How could one of the lights get to the middle before the other one does?
Because after the lights flash, the detector's back here and not in the middle.
No, the detector doesn't move.
Does it have something to do
Relative to
with
the-
that there's a red light and a green light and that they have different wavelengths? and
No,
all-
yeah, as I started writing it up there, I thought, I wonder if someone's gonna bring that up. No, it's nothing to do with that.
That's a
I
good
don't-
guess though.
That's a good one,
way to
Anna.
go.
Thank you.
That's a good
All
one.
right,
Tell us, please.
let's put this slightly differently
No,
then.
I need to be spoon fed and I need to figure it out
Yeah,
myself.
that's what we
All right,
did.
I'm gonna erase Harrison right now. Right, are those about in the middle?
Wait, what are we doing?
We're about to race.
Okay, yep.
And so, it's a race to see who gets to at least one of those bags first. All right, go.
You already started. You said go when you're already moving.
Is that against the rules?
Yeah, start though, start
Get
there.
Yes.
ready, get ready.
Why is that against the rules? What rules did I claim?
You didn't claim any rules.
Harrison, just use your telekinesis, like.
Alright, well, we need to lay down the ground rules.
Are we doing this again or no? Because I just.
Yeah, let's do it again.
Respect to the commitment.
So, for the detector in the middle, how does one light get to it first?
It moves towards it.
Say it again?
It moves towards it.
Moves first.
It has a head start.
Moves first. He's got a head start.
From Lou's point of view, they go off at the exact same time. From Sue's point of view, they don't go off at the exact same time.
Why?
Yeah, because
Yeah.
one hits one hits the detector.
This is one of the implications of relativity. Just because two things happen at the same time from one point of view does not mean they happen at the same time from another point of view. And I'm not talking about, let's say there's a lightning strike 2 miles away, someone who's a mile closer is gonna hear the thunder before I do, or see the light before I do. We're not talking about that. We're talking about, well, the situation right here where these two objects are gonna go off at different times from one point of view at the same time from the other point of view.
Is it because this light on this side? No, because the detector has to hit the middle, right?
The detector's in the middle,
Right. So, because this light hits it first, it starts first.
yes. From Sue's point of view, this side's gonna go off first, and then that side's gonna go off.
Wouldn't the same thing happen with Lou though? Because one light is going to hit the detector.
Now, I've set up the problem, it's a thought experiment, so I can do this. I'm setting up the problem so they do go off at the same time from Lou's point of view.
Okay.
I'm establishing that as, from Lou's point of view, they happen simultaneously.
Thought experiment. Okay.
So, with all that being said, that's one of the things I love about relativity. All right. Is there anything that is actually gonna be the same for everybody? Because obviously time's not the same, length's not the same, events going off at the same time, it's not the same. Events going off at the same time, depends on your point of view. There are actually two things. There are two things that are gonna be the same for everybody regardless of how fast you're traveling. One of which is,
Speed of light.
yep. If we go back to the original experiment, the original thought experiment, where we had the box moving to the right at some speed v, and we had the mirror. And the light comes up, bounces off, and then comes back. And then from the box frame, light goes up, hits the mirror, comes straight back. Light frame, box frame. This distance here, h, was the same for both. Now, obviously, I just can't come up and say, well, h is always the same for everybody because that's such an arbitrary value, but we can do better than that. This distance right here, so if the box is traveling a distance, we'll make it delta x. This distance right here would be half of however far the box travels for the whole trip. This height here is h. This from here to here, I know is that's the total distance it travels. And so the total distance it travels would just be the speed of light times however much time happened. So this hypotenuse here would be 1/2 c times the speed of light. Or try that one again. 1/2 the speed of light times how time. So I have this relationship here that 1/2 ct squared is equal to h squared plus 1/2 delta x squared. Remember, h is going to be the same regardless of the reference frame or regardless of the speed this is traveling, so I can just solve for h squared. H squared, therefore, is equal to this, 1/4 ct squared, minus 1/4 delta x squared. Since h is a constant, or whatever it happens to be for a problem, I can multiply everything by 4 and it's just a different constant. And so what I end up with is ct squared minus delta x squared. So for a particular problem, this relationship here is going to be the same for everybody. It's what's called an invariant. So for Sue and Lou, we have some distance traveled, we have some time, that if they went through the calculations and did the math, this would be the same for both of them. Time's not necessarily the same, distance traveled is not necessarily the same, but this combination is. Let's take it one step further. There's multiple derivations of this, and, all right. So I'm about to do another derivation here. I am gonna hand wave a little bit. That's not the one I had done. That's the longer, more oppressive one. Let's skip that.
See, impressive is relative, and I think the shorter one will be, will seem very impressive to all of us, because we are less familiar with physics.
Actually, I said
You said
oppressive.
impressive.
Not
Oh, I
impressive.
missed that.
Yeah.
Thank you.
Okay, bye, Sue.
Question about the delta x here.
Yes.
If we were to apply that relationship to another problem, like for example, the train problem, what is delta x referring to?
It would refer to, if I have, so I'm in a rocket ship going near the speed of light, I'm playing some sort of catch game, and I throw something up also near the speed of light, different speed than the rocket. So however fast the rocket's going relative to Earth, I now throw something that has some speed relative to the rocket. So delta x would be the distance that it travels in some amount of time from my point of view. People on Earth would also look at that and they go, well, we see it traveling a different distance and for a different amount of time. So that's what that would be.
Okay.
So speaking of which, let's say I'm in a car. Sure, car. And the car is traveling at some speed v. I have an object here that's being thrown forward at some speed, we'll just call it u, relative to the car. So this is the speed relative to the ground, this is the speed relative to the road.
To the road or to the car?
Thank you. Speed relative to the, actually, it's a directional thing. Velocity relative to the ground, velocity relative to the car. How fast is this object going relative to the ground?
I wanna say faster, cause it's like being influent, it's being thrown and then it's also going in this
Okay,
direction.
so what speed would it be?
It would be whatever speed, it would just be
You want
adding
numbers?
these two velocities.
So it would just add them?
I think so, because they're heading in the same direction.
So the velocity of, we'll just say, let's say a ball, relative to the car, is the velocity of the ball, velocity of the ball relative to the earth, is the velocity of the ball relative to the car plus velocity of the car relative to the earth. This is a legitimate, whenever you're adding vectors, as long as those are the same, this is a relationship that works, and that's the first letter, and that's the second reference right there. So the velocity of the ball relative to the ground would be the velocity of the ball relative to the car, plus velocity of the car relative to the ground, just the sum. We can also look at this from a point of view of distances traveled. Yeah, I felt like I started down a path that I wanted to do next. All right, time back to this. All right, I'm gonna just let that hang there for now. So I have my road here, and I have a car traveling by. I'm gonna establish this as my reference right here. And when the car passes this, a light's gonna go off. So by the time the light gets to the car has now traveled, and it's gotten closer to it. So now the car is here when the light gets to it. The time it takes for the light to get here is, well, it depends on your point of view. Are you talking about the car or are you talking about the ground? So let's do the ground. So we're gonna call this the ground, the S frame, and the car, the S prime frame. There's 2 points of view. So the time it takes for the light to get to the car is time t, and it's traveling at the speed of light. So c times t would be this distance right here from the ground's point of view. This distance right here would be the speed of the car times time from the ground's point of view. And this distance right here is how far away this is from zero. So we'll just call that x. I haven't said anything wrong yet. It's just a matter of how do I want that final form. How do I want to get that final form? Oh, it was up here. quickly here. I'm gonna take a moment and think. It's somewhere in this mess. All right. Okay, so this would be, oh, okay. All right. We're just talking Galilean relativity here. So how far away is the light from the car? When the car gets to the light, it's gonna, basically, anytime you see something, it's light smacking into you. We judge the distance based upon, well, the speed of light and how much time elapsed. What we have here is that x prime plus, there's a minus sign, it's gonna mess me up here, sorry. Right, so we're talking about how far what the times are here. So the time it takes for the light to get from here to the car is different from the time it takes for the light to get from here to here. So the time it takes to get from here to the car actually would be some time from the car's point of view, how much time passed from the car from the moment of zero, and it's traveled that distance. So I have Vt prime plus x prime is equal to x.